Howdy y'all, we're Team 5921 La Cañada Engineering Club.
This year, our goals were to put the 3 rings into the high goal, deliver the wobble, shoot the rings loaded on the field, and park. First, we used image recognition to see how many rings there are and determine the drop zone for our wobble. After we drop our wobble, we go up to the shooting line and fire all 3 rings into the top goal. Finally, we pick up the remaining rings on the field and shoot them in and park at the end.
Our camera is able to detect the number of rings in a stack using OpenCV. By isolating color and increasing contrast, we are able to separate the ring stack from its surrounding. After finding the area, the robot now knows how many rings there are. This also helps when there are different lighting scenarios. We use vision to detect the goal. Vuforia allows us to find the robot's absolute position on the field. Using this, we can find our way to our actual desired position along 3 different axes: horizontal, vertical, and rotational. We started off with a virtual simulator to test and write basic methods of a robot, such as driving straight and turning. We also took into account an error factor in case the robot didn't move in an exactly straight line, similar to the conditions of a physical robot. PID is an algorithm for error correction. The 3 components of the name PID stand for proportional, integral, and derivative, which combined give the output by calculating the actions a robot needs to take in order to correct itself. We also use this for a turn.
While planning for Autonomous, we decided that using XML would be the best option for us. We're able to use text files to read autonomous commands. XML lets us have multiple autonomous plans and quickly adapt. For Teleop, we'll use the controller as a way to input method commands, and each time the controller inputs something such as go forward, methods will be triggered and the robot will take action.
For our robot, driver 1 controls the robot straight, strafe, and turns, while driver 2 controls the intake, shooter, and wobble mechanism. Our velocity-based shooting and intaking allows for a consistent way to accomplish these tasks. When we notice a dip in the shooter's velocity, we stop our conveyor belt for 200 milliseconds to allow our shooter to get its speed back. In addition, our camera Vuforia allows us to track where the high goal is and when to shoot during auto, ensuring a perfect shot. PIDs are essential for Autonomous to make sure that we are on the right and straight path.
For driver 1, we have programmed the controllers so that there are different buttons allowing for the driver to move at 50% power, 75% power, or 100% of the power, allowing for the robot to make fine adjustments or move fast across the field. We also incorporated PIDs into our controller because when the driver moves the joystick in a direction relatively straight to forwards, backwards, right, or left, our code changes it so that the drivetrain moves in a completely straight direction for super straight paths. For the second driver, we programmed it so that if there's a ring that is possibly stuck inside the intake or the robot, driver 2 has the ability to control both the intake and outtake of the robot with the same D-pad. Also, we made it so that the wobble's arm's positioning is set as a button and can change the motor to act as a servo with 2 positions, an intake and an outtake. Also, when we shoot our rings, we notice that there's a dip in the velocity for the shooter. To work around this, we designed a button that automatically moves the intake when the shooter's velocity is back to speed, used to shoot the rings into the high goal, and stops to allow the shooter to recalibrate and get back up to speed necessary to get into the high goal. Thanks for watching our controller board video. Best of luck to all teams.